from University of Amiens, who is going to tell us about parabolic subgroups of complex braid groups.
Thank you very much. So I'm very honored to be the last speaker of this distinguished conference. So this is joint work with Juan González Menezes from Sevilla, plus a part which is not published yet, not available yet, but inside the ongoing thesis of Wayne Garnier, who left this morning because he didn't want to see my talk. Okay, so this is the incentive of this talk actually grew out of another work by other people on art in groups that I should mention only at the end for some reason that will appear in this talk, because we actually generalize not only the results but also the concepts appearing in the talk. So I need to build the general theory first. So the story will have three parts with quite separate ones. So first I will describe what is known in the domain of usual braid group as the curve graph, the curve complex also. Then I will ask you to keep this in your mind for the second part, which will be about something completely different. And then we will gather the two on the last part. Okay. So what is the curve complex? So I should say that this story is about an aspect of, looking at what we know about the braid groups, the usual one that you take strands and make funny pictures out of this, and what we can do for the more general case of the generalized braid groups attached to complex reflection groups. So for some, we have some techniques that have been generalized. One of the most powerful ones being the Garside theory for dealing with these groups by looking at the analogous notion to positive braids and so on. But some other tools that are available for the usual braid group are not at all available for the more general case. And one of these is connected with the description of the usual braid group as a mapping class group. So you can describe the braid group as a mapping class group of the unit disk minus endpoints. Okay, so this means the homomorphism of the unit disk, which are the identity and the boundary, and permute possibly these endpoints. Okay, modulo an isotropy relation between the homomorphisms. So this is a well-known object. And when you view the braid group in that way, you have a number of tools available, but you don't have in the general case. In particular, you have all the dynamic properties. So in particular, you have what is called the Nielsen-Thurston classification of braids, which tells you that whenever you have a braid, either it's periodic, which means that some power is central, or it is reducible, which means that you can prescribe some curves here and there so that your homomorphism more or less preserve that curve, roughly speaking. Or it has a very nice dynamical property, which is called pseudo-anosov, which can be nicely described in terms of the surface, the limit of the surface, in terms of foliations and so on. So things which are completely different aspects with what we are used with when we deal with generalized reflection groups. I will describe one specific aspect connected to the fact that the braid group acts, what is called the curve complex or the curve graph, that Bien described in this way, so that acting on this disk will act on every object that we can define inside Dn, under the condition that it is well defined up to homotopy, because we have our braids, which are homomorphisms, but only up to isotopy. Okay, so what does it mean? So typically, if you take a simple closed curve, there in your disk minus endpoints, okay, if you apply braid, used as an homeomorphism, it will change this into another simple closed curve, okay, containing the same points. And so this will be preserved, except that your curve is up to homotopy. Okay, it's not really acting on the curve; it's acting on its homotopy class. And you want to don't look at the degenerate cases, like if my curve contains only 1 point, then it's not a good it's up to homotopy, it's just shrinking to a point which is not to be there, so it doesn't mean much. So what we call an essential simple closed curve is a simple closed curve which contains at least 2 points. Okay, so I give you 2 seconds just to be sure that you don't have any question about this thing. So probably many people knew about that, some don't. So do you have any question about this? It's okay. Okay. So what is the curve complex or the curve graph? So the curve complex is simplicial complex, which is defined as the flag complex or the Clyde complex of a curve graph. So basically, the main data is a curve graph. It's really a graph. Its vertices are all the simple closed essential curves you can draw on this picture up to homotopy. Okay, so these are your vertices. And when you want to define, so let's talk about the simplicial complex. What is the face in your simplicial complex? Obviously, it's a collection of vertices. And the collection you consider are the collection of simple closed curves, the essential ones, which do not intersect pairwise. Okay. So of course, this has no meaning because it's up to homotopy. So you need what it really means is that you can find a collection of representatives of your homotopy classes such that they do not intersect. Okay. So this is a typical case here. So we have these 2 simple closed curves, they don't intersect, and that's fine. Okay. So this provides for me an edge in my simplicial complex because I have 2 such simple closed curves. And actually, if you think a little, you see that only the one skeleton is relevant. When I have my curve graph, meaning that I look only at the edges, then the simplicial complex is a Clyde complex associated to that. Okay, so this is the object that has a very interesting structure and which is associated to this vision of the braid group as a mapping class. So yes, another example here. So you see here, I have a face of dimension 2. Okay, I have a simple closed curve here, which is on this side, and then I have another simple closed curve, which is inside another one. So these 2 are nested. Okay, so we'll see this kind of these various kinds of behavior play a role later on. Okay, so this is our curve graph or the curve complex, yet another one. So you can have also a face like that. So it's fully nested like this. This is another example. What happens in the curve complex. So the thing is that you can, so as I said, the braid group will act on every such object well defined up to homotopy. Okay, so in particular, it will act on this simplicial complex or simplicial graph. And it acts almost faithfully. Well, the only thing is that you have to divide by the center. So what I mean by almost faithful. Okay, so it's really you have a geometric object, natural one on which the braid group acts, and one of the nice aspects of that complex. So I think Maser is with an S and not a Z, but is that it's if you put on this natural geometry. Which means that you take the geodesic length on the curve graph, then one can prove that it is delta hyperbolic, so in the sense of Gromov, which means that the triangles are thin, so that there is some delta, such that if you have a geodesic triangle there, then for every point in the union of 2 edges, then you have some point on the third one, which is as distance at most delta, right? So it's a very, very nice property, which has some consequences. I mean, people in geometric group theory like to have groups acting on hyperbolic spaces because they know to do a lot of things out of that from a dynamical point of view. Okay, and I just remind you that, for instance, the Nielsen-Thurston classification I took as an example is about having dynamic properties. Okay, for the pseudo-Anosov description. Okay, so this is what we are lacking so far. One of the things we are lacking when we want to study the generalized braid groups. Okay, we don't have a priori this kind of stuff. Okay, so that's the end of the first part. With this open question, is there a generalization of this complex to the generalized braid groups? Okay, so now there is a break. And we're going to the second part. Okay, so forget everything. Just put this in your memory. We're not talking about this for the next 10 minutes. Yes, Emmanuel?
Say the complex is determined by the one skeleton. You mean it's a flag thing?
Well, technically it's flag complex. I think there's a subtle thing between the flag, between the flag and the but yes, it's the idea. Yeah. Okay. Other questions? Okay. So parabolic subgroups. So okay, these are my notations for the usual objects, you know. So W is complex reflection groups or pseudo reflection groups, or no, complex pseudo reflection groups. There, A is its hyperplane arrangement. I will denote X, the corresponding hyperplane complement. It's elected upon by W. So there are two groups associated to that. There's a pure braid group, which is the pi1 of an hyperplane complement, obviously. The braid group, which is a pi1 of the orbit space. And we have a short exact sequence, and I will keep the notation pi here to denote the projection, which will play a role later. Okay. Obviously, well known when we have the case where W preserves a will form, then we have a nice Coxeter and Artin presentations for W and for the braid group. Okay. And we have a very important concept inside the reflection group realm, which is the concept of a parabolic subgroup. Okay. So in that case, a parabolic subgroup of W is defined in general as some pointwise stabilizer of the natural action of the power of W on C2Vn. Okay, so this is a very nice notion that we all know. I mean, if we didn't know this before going to the conference, now we know. And it's in the collection of such parabolic subgroups is in one-one correspondence with the usual lattice associated to the reflection arrangement, because whenever you have such parabolic subgroup, you can consider its set of fixed points. That's a flat in the intersection lattice, and conversely, starting from a flat, you can look at all the pointwise stabilizer. So you've got group theoretic or geometric description with a description of myths and joints, which is equally easy on both sides. Okay, on the group side, you take the intersection, and you take also the smallest parabolic subgroups containing the union. So this is really easy to describe there. Okay, so what we want to do for some reasons, which is partly connected to the first part, is to lift this concept of a parabolic subgroup for the reflection group to a concept of a parabolic subgroup for the braid group. Yeah. And so we have the parabolic subgroup is the reflection group. So there is a braid group attached to it. Okay, let's call it B naught. And we want to see this as a subgroup of B. So we want an embedding. And from the geometry of the hyperplane arrangement, it is reasonably easy to see how one can do. So first of all, recall that there is a base point attached to the description of B. So I have a base point there. Okay. And then I look at what is fixed. Let's call it E, the E corresponding to my parabolic subgroup. It contains, well, all reflecting hyperplanes of W naught. Okay. And then what I can do is that when I pick a generic point on E, I take a ball omega around it. Okay. And if you zoom there, this small ball, does not cross any other hyperplane, then it's homomorphically to what will happen if only W naught was there. Okay, so this space here, it's a reduced version of the hyperplane complement for W naught. Okay, so if it's pi 1, if I take the base point around here, it's just B naught. Okay. Except that I need to connect this to the main space. So I really need to take care of the path here. Okay. But I can do this that way. So I describe this only at the level of the pure braid group, but you can check out that it works. We can extend this. Okay. So far, so good. So this is what I just said. So in case I wasn't clear. This is what I explained already, except for the last slide, the last line, which what is interesting with that is I have defined attached to my W naught, so the parabolic subgroup of W, I have attached a conjugacy class of subgroups. Okay? Because of this choice of a path from my original base point to my ball, for instance, plus the fact that I chose my ball here and not there, you know. So there's things to, but what is well defined is just this conjugacy class of subgroups. Okay. By the way, for people doing Echo algebras or Sharonic algebras, this is also something your parabolic braid group is defined only up to conjugacy. This has no meaning in general to define this like that. Okay. Okay. So this is what I want. I'm happy. Well, maybe not completely. The problem is the following one, is that what we want to consider is really the braid group. And the braid group does not depend only on, well, it doesn't determine W. You see, W defines your hyperplane arrangement. But when you pass to the quotient, you define a space which can be obtained by various reflection groups. Okay, this is a concept of isodiscriminatality that we already talked about. Is that you know that by Chevalier-Shepard theorem, the quotient of C to the n by W is actually homeomorphic to C to the n. Okay, and in that way, the orbit space is a complement in C to the n to some hypersurface, which is called the discriminant variety. Okay. And what we really are working on is the pi 1 of this space. And in this space, it may be that you have the same discriminant, so the same space for two different reflection groups, which have completely different intersection lattices. Okay. So that's the same problem. So for instance, if you prefer true reflections instead of pseudo ones, then you can always find for each W a W prime, or each W1 a W2, whose reflections all have order 2, and so that you have the same space. This is what has been used by David Bessis in particular to complete the K-pi1 conjecture. Okay, so the problem is that our definition of a parabolic subgroup actually relies on the hyperplane arrangement. Okay. So we want something that depends only on this topological pair, actually. We need that because these are already homeomorphisms. There's no more than that. It's homeomorphism. Okay. So this means that what we are really dealing with is still a base point somewhere, fixed once and for all, some discriminant here, some point on some strata here, okay? And we need to define a parabolic subgroup as the image of some so-called, well, maybe what you may call a local pi 1 there, inside there, and said that you need to be very careful with what you mean with that. And so I won't go into details. Just say that you start instead from neighborhoods inside C to the n minus z, neighborhood of the point you've chosen, and you take the image of pi 1 of u inside B. And if you're a bit cautious, this doesn't mean anything because my pi 1 needs to have a base point attached to it. So if I take the base point in U, well, when my U restricts, it's not well defined and so on. So you need to take a projective limit there. And then you know it works because you have your previous description. So I don't go into details here, but there is non-trivial way to define this concept of parabolic group in that way. So this is done in our paper. And this is the general notion we need to define that. Okay. Okay, and then nice things happen. So the image under my pi of a parabolic subgroup defined this way is obviously a parabolic subgroup of W, because actually it turns out it is the same. That's the one you obtain by doing the other construction if you have chosen a specific parabolic subgroup providing this discriminant description. Okay. Any questions so far? Yeah, I spent only 20 minutes there, so I think it's been a bit fast. So let's say 10 seconds, no, 2 seconds. Questions? 2 seconds and a half. Okay. So what you can prove out of the blue from this definition, just using the topology, are the following things. If I have a parabolic and I conjugate this parabolic of B, right? So B naught. And I conjugate this by some element G, and the conjugate is a parabolic. So it really defines a class of a conjugacy class of parabolic of subgroups. If I take two parabolics corresponding to parabolics of the reflection groups, my BIs are mapped to WI, then I can check whether these are conjugated in the braid group by just checking whether the image are conjugated inside W. Okay. There are natural questions. I have B, my group. I take B1, a parabolic of B. By B1 is again a generalized braid group. So it may have parabolics. So are the smaller ones parabolics of the big ones? Okay, that kind of questions. So everything goes fine. Similarly, if I take this kind of things you need to check if you want to get a working theory, and it works. So probably we are on the right path. And we have defined then a lifting of the concept of the parabolic subgroup from the reflection group to the braid group without using anything but the topology of the space. Okay. Okay. So we have the right-hand side of your head as parabolic subgroups of the braid groups, your left-hand side as the curve complex. Now we mix together and we are trying to describe our main results there. So the parabolic subgroups of W, we know that they form a lattice. For the simple reason that it's the same structure as the intersection lattice for the reflection group. Okay. And our first theorem, main theorem, which is very long to prove, is that we have this quite curious, unexpected property there. If you look at your parabolic subgroups of B, if you intersect the two of them, so we make an intersection of subgroups without anything else than pure group theory, then these are parabolic subgroups again. So that's one of the main theorems. So I will give at the very end of the slide some ideas of the proofs, but they are very involved. And this has the following consequence, which is that if you take a braid, so attached to things, when you can say that there exists a unique minimal parabolic subgroup containing it. Okay, so you can attach to every braid a parabolic subgroup. So this is what we call the parabolic closure of the braid. And proving the theorem is almost as difficult as proving the corollary, so it's not a simple fact, this one. Okay. So now the connection between the right-hand side and the left-hand side should be done, because now we are really mixing the two. Oh, not yet, sorry. I need to state the one. I need to recall also some basic results of the center of the complex braid groups. So the braid groups attached to a complex reflection group. For this, you need to recall that in general, when you have the complement of some collection of hypersurfaces, it is in general very difficult to compute the center of that. In particular, for hyperplane complement, it's very difficult to compute the center of the pi one there. Just to give an idea, if you have in C2Vn and you have a divisors with normal crossings, this is a difficult theorem of Fulton saying that the pi one is abelian. It's really not what you usually have, is that you know that some paths will obviously commute, but determining the center itself, they are not really very well. It's very difficult in general to have geometric meaning to attack that. So in particular, even for the pure braid groups attached to Artin groups, in general, what you do is that you use the monoid structure on the full group in order to get the center of the pure one. So this is in general not easy at all. So, but in this case, we know what is the center. So this is what I will describe. So first, I recall that B has no torsion, okay, for a number of reasons. Either, but you know that that's a orbit space, a pi one, or by combining things using Garcet theory and so on. So now we assume that W is irreducible. Okay, we can always suit to that case because every reflection group is a direct sum of irreducible ones. So in that case, by Schur's lemma, you know that the center is generated by some root of unity that I will denote small z sub W. So it's some exponential 2 pi I over m. And from that number, you can define obviously central elements in your groups P and B. What do you do? So my star here is the chosen base point, and I take a full loop around it. So since my hyperplane are linear, and that I took my base point outside of the hyperplanes, well, of course, every multiple of that will sit outside the hyperplane. So this is a well-defined loop. And it's easy to check that it commutes with everything. Inside B, if I take this path, so this means I don't go from t from 0 to 1, but I stop at 1 over m. Then at t equal 1, I will have the image of my star under this element of W. So this is a path outside my hyperplanes, but will becomes a loop in the orbit space. Okay, so this is Z sub B. Okay, and then what was a conjecture by Boehmen and Rouquier in 1998, where they studied this and proved much later on. So thanks by using works of Boehmen, Rouquier, Bessis, and then my paper with François and Jean-Michel, we completed this conjecture of Boehmen and Rouquier that the proof that the center of B is cyclic generated by the obvious element. Center of P is cyclic generated by the obvious element, plus we have a short exact sequence. But what we really want is this result, that the center, in a purely group theoretic way, is exactly what we think it is from the geometric situation. Okay? So if I'm not wrong, now is the time to connect two things. Yes. Okay. So what is the connection between the two? Okay. So now I'm going back to the usual braid group and see what parabolics have to do with curve graphs. Okay. So consider some essential simple closed curve C. Okay, something like that. Okay, so by Jordan theorem, it has an interior and an exterior. Okay, and I can consider all the homomorphisms of the disk, that are the identity outside of the curve. Okay. This is a subgroup. And as you might expect, this is a parabolic. But we don't go till there already. So we have, for now, I use the notation B of C to describe this subgroup, okay, which acts trivially outside the curve. And I want to interpret what it means that I get C1, C2, two simple closed curves that correspond to different vertices in my curve graph. What does it mean when they are adjacent? Okay, that they are connected. So how do I do that? Actually, you can check that if they do not intersect, so this means that we can put them in a way that they are not intersecting, then in terms of the group, we are in one of the two following situations. Either they are nested, one is inside the other, okay? And this means that B of C1 is inside B of C2. Okay? This means that if I act trivially outside this curve, and of course I act trivially outside this curve. So this corresponds to a connection to a property of that form, inclusion of subgroups. The other situation is when the interior of one is inside the exterior of the other. Okay, so we describe non-intersecting regions in the disk. And it turns out there is also a group theoretic characterization of that, which is that these corresponding two subgroups should have trivial intersection and they should commute to each other. They should centralize each other. And it turns out you can really describe the curve graph for the braid group by using this group theoretic description. So this is not always a very common, a very useful, a very handy one, but we'll see later on a more handy description of that thing. But as you see from that description, it's enough to generalize the curve graph. Once we have generalized the parabolic subgroups, because this, as I said a bit before, is that these subgroups are exactly the irreducible parabolic subgroups of Bn, as I said before, meaning irreducible, meaning the parabolic subgroups which maps onto irreducible parabolic subgroups of the symmetric group. Other questions so far? Okay. So this is what I just said. So the curve graph in general, when defined by these vertices, adjacent, and of course, we are optimistic people. So one can check that B over set of B acts again faithfully. Okay, so how does it act? Just by conjugating the parabolic subgroups. Okay. Obviously, the center of that acts trivially, but we know the center now, so it's not a problem. And we conjecture that, which is a thing which is also proved in the case where we have a mapping class group type of interpretation for the thing in types B in Artin type Bn, for instance. But for now, it's difficult to prove that from the tools we have at disposal. Okay. So we have an alternative, as I more or less said already. We have an alternative announced already. So we have an alternative description of this graph in terms of the central elements. So, okay, I realize I don't remember. Yes, if you remember what we denote the Z sub B is a natural generator of the center of the braid group in case it is irreducible. Okay, but here we're considering only irreducible parabolic subgroups. Okay, so they have very natural generating elements in their center, which is Z sub B naught. Okay. And one can prove that this B naught is exactly the parabolic closure of this. Okay. So this is what B naught is the smallest parabolic subgroup containing it. And then we have a nice description, I think, of this adjacency relation that was before that in terms of inclusion of subgroups, of normal centralizer, and so on. In order to really define the graph, you just need to check whether the corresponding central elements of your parabolics commute to each other. Okay. And you have also a way to describe the action of the braid group on this collection of vertices by just looking at the actions on these elements. So this writes for you another description of the curve complex purely in terms of elements of your braid groups. And this has the following corollary. So if you want to compute things inside your braid group, one thing which is rather easy to do by using Garside methods is to compute centralizers. Centralizers, it's possible once you have a Gaussian structure, that kind of stuff, you have tools to do that. But this tells you that you can also get normalizers of your parabolic subgroups by computing the centralizers of these. So this is something which is quite handy if you want to do specific computations of normalizers of your parabolic subgroups. In the case where we have a Gaussian monoid to control stuff. Okay. Okay, it's already almost finished. Okay. So, have any before I talk about the proof? Any question? No. Yes.
I mean, is it possible to interpret the Nielsen-Thurston description?
Okay. You can interpret the Nielsen-Thurston. Okay. So the Nielsen-Thurston description tells you that you have either periodic elements. So this is easy to generalize because you can define a periodic element as something whose power is central and you know the center. Okay. And then you can't define pseudo Anosov by a positive property so far because you don't have, well, you should, in order to do this, you should define equivalent, well, something corresponding to foliations and so on inside the curve graph. So I don't know whether it's possible, but it would be the nice stuff. In order to define reducible braids, then you can say that these are the braids which belongs to the normalizer of some proper parabolic. So yes, we can define this trichotomy, but what we need is having a control on the dynamic of what are these elements which are not periodic and not in the normalizer of the parabolics. And this is related to understanding better these things so that we can prove hypervelocity and other property. Other questions? Okay, so the proof. So there are several steps. So we need to, like every single property concerned about complex braid groups, we need to really understand by using the classification different types of groups and what tools we have to prove things about them. So first thing, we choose in each case an appropriate W generated by reflection of order 2 most of the time. Well, all of the time actually. No, most of the time. So that to concentrate our proofs, okay? So we don't need to take, for instance, when we have Shepard groups, we can just look at Coxeter groups. That's okay.
What do you do for the others?
For
the others?
That's the other steps. No, you mean for reducing to the case of groups of
Choosing the W.
Okay. Before I do that, I just noticed in my slides that there is a gap between 1 and 2. So I will answer to Y prime and then I go back to your question. The Y prime, which is not there, is that sometimes what happens, especially in the infinite series, is that your braid group.
In number 2?
No, because I want to do 1 prime.
Okay.
Which is not there. And so in that case, it happens that your braid group may be a normal finite index subgroup of another one with cyclic quotient. This is the case for the G, E, D, E, N, and so on, for instance. And in that case, you do specific arguments to check that you don't need to deal with these. Okay, so you have a large class of things that is already a reduction. And once you have done that, so you get rid of what is intermediate in the infinite series, okay, by this argument 1 prime. Then you use this reduction, and then you are maybe sometime. What remains are the GR1N, the GEN. These ones are isodiscriminational to this one, which is our group of type BN or CN. Okay. These ones, they remain like that in the infinite series. And in the exceptional ones, the Shepard groups, they are Coxeter. And then you've got exceptional ones which are 2 reflection groups. Okay. So this is the reduction we do at this step. So I guess this under question. And then for all these cases remaining here, except for G31, it was proven that there exists a nice Garside monoid and even an interval Garside monoid. So in as you learned about in George's talk yesterday, with nice properties. So in the case of wheel reflection group, you take the Artin monoid. Case of Shepard group is the same because okay, you already made the reduction. In this case, you use the Picontin monoid, standard monoid described by George yesterday. So this corresponds to a diagram which is usually presented as a circle like that. T minus 1 here. So you have a circle that represents a dual braid relation between these generators, and then you've got additional generators there. So depending on your mood, you can call this a parachute or an umbrella, depends on the text. Yeah. And this is a very nice monoid that shares a lot of common properties with the Artin ones. So we use that in that case. In the case where you're looking for exceptional groups in higher rank, except for G31, you can use generalization by basis of the dual braid monoids. And in that case, what you need to check, that is true, is that the parabolic subgroups that we define topologically are the ones that you would expect from a monoid description. Because when you're looking at the parabolic subgroup in the top set of case, what you do usually is that you take your diagram, you pick a number of generators, you call these the standard parabolics, and then you take the conjugates of all these. Okay. But then what we prove is that actually this purely monoid description of the parabolic subgroup, which is heavily dependent on the choice of the monoid, and therefore the choice of base point, actually corresponds to our topological description. So in particular, if you take a description of a parabolic by using the Artin monoid, and by using the dual braid monoid, these parabolics are the same because of our topological description. Okay. So this is how it goes. And then, well, okay, you have now some tools. So how can we prove these properties of intersection and so on by using these Garside monoids? We need to prove additional properties that I don't want to go into, proving that if our Garside monoids have this and that property, then we can define parabolic closures, things like that, like this, with the definitions. And the fact that system of parabolic closure is one of the main aspects. And at that point, in order to really make intersection works, Garside methods are not enough. And we need to prove something silly, which is, okay, which is the following one. You see, we want to interpret the fact that the two elements we've chosen as central elements of B1 and B2, when they commute, we want to prove actually that B1 is inside B2 or B2 is inside B1 and so on. That's our main goal. But already actually what we need to prove is that this is the case for the image inside the reflection group. Okay. But if these two elements commute, the either W1 is inside W2 or the other way around, or they are that don't intersect trivially and commute together. Okay. And in order to prove this, actually, you can prove this case-free, but in spirit, morally, what you do is that you compute inside the Echo algebra. Except that you don't need to introduce the Echo algebra. You use the non-linear representation associated to it, and then you have a specific another argument. I just say this because it's an argument of a different type than the rest. Okay, and then for G31, there's the same problem. But for G31, the only graph we had on the corresponding braid group is to embed this as a centralizer inside the Artin group of type E8. The same thing for the K-power conjecture and so on. And so, so this means that for that, you need to use a Garside category, which means that you need to redo everything in the Garside category setup with many new arguments in order to deal for this case. And this is the contribution of Owen Garnier, which is a very great one. Okay, and then just to finish, I promised credits. So in the real case, what was an incentive of the work, the original one, was this work by Juan and also Maria Cumplido, who was a PhD student of Juan and Bert Wist, together with Foucault Gebhardt. What they did was obtaining these results in the case where you are for real reflection groups, but moreover, you define parabolics as in a combinatorial way. Okay, so this means that our result is a bit larger concept and also generally something more general than their result in the case of the real case, but there's really an incentive of our work. And I think I'm exactly the time. So as I promised to Alex, was a plane to catch, and so thank you